In this recording, we're going to learn about the number e and the natural logarithm. As it says here in the opening paragraph, there are many numbers in math that are more important than others. They have really important uses in math and science. And some good examples of these are numbers you're already familiar with. The number 0, obviously, 1, I, the imaginary unit, you learned about this here, and pi. And in this lesson, we're going to start to get acquainted with the number e. And it's so named E for its inventor, Leonard Euler. Kind of an odd pronunciation there. And you're going to learn more about this number in this course as well as in later math, pre-calculus, calculus. It's very useful in modeling exponential phenomena. So, you know about pi. Pi is not intimidating anymore. You know it is irrational. It goes on without repeating. You're familiar with 3.14 or 159. Maybe you know a little bit more than that. I'm not sure. E is also irrational. It does not repeat, does not terminate. It's a constant. That's why you've never seen a variable written as E. You know, we solve for E, we always solve for A, B, or X, right? And it's about 2.72. Right? We can go to our calculator and evaluate it. It has two places. It's here, above the division key, but it's so often used as a base that it's also here. So you could do like E to the 1. And so anything to the 1 is itself. So 2.72-ish is the value of E. It's used in exponential modeling. So given that it is that, which of the graphs shows e to the x? So think on that. Pause. Play the recording when you're ready. Okay, so I'm hoping you recognized that it has to be an exponential. Okay, so it's either 2 or 3. It's not going to be a parabola. It's not going to be a cubic. And it's exponential growth. Well, why? Well, we just said it's 2.72. It's bigger than 1, so it has to be exponential. Now, when we talk about e in terms of modeling, we're often going to use e as a base of exponential models. And these could be models to do with exponential growth or decay. And to know if it's growth or decay, you simply look at that exponent and see if it's positive or not. All right? Because the base is always positive. So we know that's only going to make growth if the exponent is positive. But if the exponent is negative, that reflects it across the x-axis, right? Excuse me, the y-axis. So that makes it an exponential decay. So let's check out this Llamas problem. Why don't you go through and underline the important stuff in the question, and then fill out part A and play the recording when you're ready. Okay, so hopefully it's obvious to you that we're looking for when t is 0 here, we're going to substitute in. All right, and this should be easy stuff. Anything to the 0 power is 1, right? So e to the 0 power is just a number to the 0 power, so that's just a 1. That's going to give us 500 times e to the 0, which is like 500 times 1. You should always label when you have a context in here. So we have 500 llamas. All right, the one on the right side is a little more complicated because it's not just a sub-in answer. We're actually solving for an unknown amount of time. And here's the really cool thing. I saw this on a website one time. It said, you have these two functions. These are inverses of each other. E to the x and natural log of x, right? And it's a little scary. Natural log of x and e to the x. These are unfamiliar things. But e to the x is just growth. It's saying, all right, after x amount of time, how much growth has there been? That's what we want to know. And then natural log of x is the inverse. It's saying, okay, how much time? It solves for time, right? So natural log says, all right, how much time did it take to get to that value? All right? So those work in opposite directions. So right here we're looking for when the population reaches 600. So play the recording when you're ready, sub in that 600 somewhere, and do as much as you can. Okay, so hopefully you subbed in 600 for the population. All right, so right now we're going to solve for an unknown exponent. And the first thing we do, have to get rid of this coefficient, right? I have to get the exponential portion isolated. So let's divide. At this point, I can leave it as a fraction, but this is a rare situation where it actually divides out nicely and gives me a terminating decimal, so I'm just going to write it as 1.2, okay? Now we're kind of stuck. And what I tell students is when you're stuck in exponential form, put it in log form. When you're stuck in log form, put it in exponential form. So right now we've gotten really familiar with going between those two forms. Let's go ahead and write this in logarithmic form. So we'll write it as log. Every log has a base. Well, what's the base here? The base is e, and I've just barely gotten comfortable with e, but I know it's a number about 2.72, right? Log base e. I'm going to leave a little space. Log is an exponent. So the exponent is 0. I guess I left too much space. There'll be a crazy amount of space there. Let me back up. So a log is an exponent. So that's what the log is going to be equal to. And then the 1.2 just comes in here as the argument of the log. What's on the left side is just a number, right? And what's on the right side is just a number times t, which I want to solve for. So now I'm just going to divide. Now, if you're really sophisticated, log base e can be written as natural log. That's what it is. So natural log has a special name, log base e. All right, so I just got that divided by 0.035. That's what t is going to be. Now it's just number crunching in your calculator. So put that right in your calculator. Natural log of 1.2 divided by 0.035. Came out about 5.2 years. It said around to the nearest tenth. Just do that. Quickly equal sign. And the last piece is I want to verify my answer. Am I right? People say, I have no clue. Well, let's have a clue. If this is the amount of years that it's going to take to reach 600, remember we said natural log tells me time to get to a particular value. E to the x tells me growth. In this case, the amount of growth after time 0, which was a trivial question. Let's go to our calculator and check. Okay, so I'm going to put in my initial 500 times e, so second, and then the ln key, to that exponent, which was 0.035 times, well, go ahead, I'm just going to put this full answer in. I'm just going to cursor up on top of that answer, hit enter. I'm not going to bother to retype it all. It's going to be very precise. Well, sure enough, 600 is, so it checks out. Thanks for watching.